So we're going to talk about concentration inequalities in various contexts. So the typical context we have in mind is when xn is a sum of psi i's for I from 0 to n minus 1. And for example, we looked a lot into IID random variables that have some type of regularity condition. So what do I mean by regularity conditions? I mean that, for example, it could have exponential moment that is finite. So e to the exponential of e to the theta psi, finite for some theta. So some type of regularity conditions. There could be others. But what we're going to do now is, instead of looking at independent and identically distributed random variables, during this course we're going to relax this hypothesis, because it's not always the case that we're trying to bound a sum of IID random variables. What we're going to relax in this lecture is the condition that they are identically distributed. So in this short lecture, we're going to talk about concentration again, but of non-identically distributed sums. And the regularity condition that we have is also going to be slightly different. So let's state our main theorem for today. Suppose that we have as above psi I and so on independent random variables. And let's assume a very strong regularity condition that xi's are always between 0 and 1. So this is a uniform bound on all the xi's. And observe that this seems like too particular of a condition, right? We're talking about being bounded between 0 and 1. But as soon as something is bounded between A and B, you can make linear transformations that make it bounded between 0 and 1. So it's not these values are not the problem. What makes this condition very strong is the uniform boundedness. So we have this xn, and again we want to bound the probability that xn deviates from its expectation by more than nt. So we can't write the expectation anymore as n times the expectation of psi, because this is only in the identically distributed case. But in any case, we are going to have mu, which is just the expectation of xn, be given as an implicit parameter. If the xi's are IID, mu is going to behave like a linear thing, like p times n. But this is not always the case. Maybe this could behave like n to the 3/4 because we are not summing identically distributed random variables. So it doesn't matter. We're going to put the expectation of xn here, and we're going to bound this by 2 to the 2 times e to the minus 2 n to the t squared. So you see that again we are getting, of course t has to be non-negative here. See that we're getting something that decays exponentially in n. We're getting a very explicit exponent here, which in some cases, believe it or not, is optimal. Not always, but it's a pretty good exponent we're getting here. And one interesting thing is that this is an exponential decay, even if this is not linear, because we're requiring the deviation to be linear. Even if the expectation is not linear, it could accumulate towards 0, but the deviation we are looking for is linear, and we're getting this exponential decay. Okay, so this is a nice theorem about deviations in the non-IID case, and we start the proof. So the proof is again something very repetitive. We're going to take exponentials and use Markov, but there's always some twist to the proofs. Let's pretend that this thing is IID for a moment and call P the average, the mean over N, and Q1 minus P. So we are almost like saying, now imagine that this was a sum of IID Bernoulli random variables with parameter P. Of course it's not, but this is going to make our notations more streamlined. And as I promised, we're going to take exponentials, expectations of exponentials, as we did before, e to the some h times h times xi. So we did this before, but what we're going to do now is not to say that this is the Laplace transform and try to get an explicit bound on this. What we're going to do is use convexity. So what are we trying to integrate? It's e to the h times something. So this is a function that looks like this. It's 1 here, and it grows like this, and it's a convex function. And this something that is playing the role of x is xi, which is between 0 and 1. So we only have to look into this. And observe that the convexity tells us that this line here is strictly above the exponential in this open interval. So what we're going to do is to bound e to the hx by 1 plus x times the slope, which is the value here, e to the h, minus the value here, minus 1, over 1, which is the size of the interval in the x-axis. And this can be written as 1 minus x plus x e to the h. So we're just using convexity to get this bound, and we're gonna plug this into the exponential moment. So this thing here is smaller or equal than 1 minus the expectation of psi k, because we're taking the expectation here, plus the expectation of psi k times e to the h, which is what happens here. Now, the expectation of psi k is starting to get difficult to write, so we're going to just call it pk. Pk is the expectation of psi k, and p is the sum of pk. Okay, so now we can rewrite this as 1 minus pk minus plus pk e to the h. So we have this explicit bound on the moment generating function of psi. Now, how does this translate to the moment generating function of x, right? So we want to at some point to estimate this e to the hxn, and this is just the product, right? Of e to the h psi k, psi I in this case, and of course the expectation of this, we are not assuming that they are identically distributed, but we are still assuming that they are independent. So this becomes this of the expectation that we just estimated to be 1 minus pk plus pk e to the h. So we have this explicit bound, and what is magic about this now is that we can first do something trivial here, just raise it to the power 1, and we wrote 1 as 1 over n times n, and use the fact that the geometric average is smaller or equal than the arithmetic average. So this is smaller or equal than, so here we are taking the product to the power 1 over n and raising to the power n. So this is smaller or equal than the sum one minus pk plus pk to the h, sorry, e to the h over n to the n. And see here, oh, by the way, I made a mistake here. This is over n, because we defined p to be mu over n, and this sum here is mu. So what we have here distributes, and we get exactly 1 minus p plus p e to the h to the n. So that's the nice thing that we obtained. It's a very explicit bound on the exponent, the moment generating function, that has the n on the outside. That's what we always want. The n doesn't interfere. And now we can calculate the probability of deviations. What's the probability that xn minus mu is larger or equal than nt? This is what we want to bound in the end. This is bounded by the, of course, we first take e to the h on both sides. This is a monotone function. And we get the bound by Markov's inequality, that this is bounded by 1 minus p plus p e to the h to the power n. And here one has to observe that this is actually the exponential moment of just x. So let me rewrite this to make it more clear. This is the same as the probability that x is bigger or equal than mu plus this. So here we're taking the moment generating function of x as we estimated there, and we still have the e to the minus mu plus nt. And recall that mu, we are writing this as np. So here we can write p plus t times n. So now I have everything raised to a power n, which is what we look for in the final statement. So I'm actually going to emphasize this by putting the n here. And all we have to do is show that what's inside here is bounded by what we claim it to be. So in the end, we want to say that this is smaller than what's here is smaller or equal than e to the minus 2t squared, and we'll be done. And recall that we still get to choose h, right? So for some h, this will be smaller than e to the minus 2t, and we are done. What follows now is a very boring optimization procedure. We have to optimize the inside here to get the desired bound, but the mystery is over. There is not much of an idea going on. So how do we optimize this? I'll not go through the take the derivative, make it equal to 0, and guess what? I'm going to give you explicitly what the optimizer is. So take nh to be such that e to the h is equal to p plus t 1 minus p over p times 1 minus p minus t. So it's a terrible formula, but it is what it is. It's an implicit thing. Note that the right here is something bigger than 1 because in the denominator we are subtracting more. And here is also something bigger than 1 because in the numerator we are summing t. So this is bigger than 1. So we can definitely write this with an h bigger than 0. Okay, we chose our h. Now we have to rewrite what's here. Let us copy it without the n. So we have 1 minus p plus p e to the h, e to the minus p plus t. This is what we want to bound in the end. And what we're going to do is replace our choice of h and see what it gives. So this is equal to, we can always keep the power n here if we want, but what we have here is 1 minus p plus p times this, but the p will cancel. But let's write it. And we still have e to the minus p plus t here. Okay, so here the p will cancel. And we're gonna explicitly perform this sum. So you get in the numerator 1 minus p, which is actually q, times 1 minus p minus t, plus p plus t times 1 minus p over the same denominator, 1 minus p minus t. Okay, not pretty, but we're getting somewhere. Let's copy this to the next page. So this is what we want to bound. We have some cancellations going on here. You see that 1 minus p is multiplying something both here and here. Here it's multiplying p plus t. And here it's multiplying minus p minus t. So this, and this cancels. And what we end up with is 1 minus p plus p plus t. When I crossed this, I only crossed, oh, sorry, yeah. No, it's 1 plus p, it's correct. It's only 1 plus p, yeah, right, over, it's 1 minus p over 1 minus p minus t. So what are we missing here? We still need just a second. Okay, I see what I'm missing. So there is an h that I missed from here on. So here we have e to the h here. So there is an h here all over. Okay, so we can fix this. And now we have e to the minus p plus t, but we have an e to the h. And e to the h, as we know, let's go back here. It's, sorry, p plus t, 1 minus p, over 1 minus p, 1 minus p minus t. So this is the e to the h that was missing. So let's do some calculations here as well. What we have is, so first we could just invert everything here. Let me not try to use copy and paste. So here we have q, right, over q minus t. This part we already simplified it a lot. Now this part we're going to invert everything because there's a minus here. And here there's also q. And now we can write p plus t here. We remove the minus simply. Now you see the way we wrote this, there is a q over q minus t here and q over q minus t here. So you can pass this part to the left because it's the same thing being in the exponent. And you get q over q minus t to the power 1 minus p minus t. And now the right is p over p plus t to the p plus t. Now look at the nice symmetry you have here. So here you have q over q minus t to the q minus t. So the denominator is appearing there. And you have p over p plus t, and the denominator is again appearing in the exponent. So this is a nice symmetry. It happens also when you're using making large deviations for Bernoulli random variables. This always appears. And recall that we're trying to show that this is bounded by this, right? Up to now we did exact calculations. And we want to show it's bounded by this. So you're going to actually treat the logarithm and show that the log is bounded by this. Okay. So what's the log of this function? So define f of t to be the log of whatever is here. Q over q minus t to the q minus t, p over p plus t to the p plus t. Okay, the logarithm behaves very well with this. It's going to first split this into a sum, and it will bring the exponent down. P plus t times the log of p over p plus t. So this is convenient. And this function f, we can estimate it using Taylor expansion. So first, what's f of 0? So if we plug 0 here, we are going to get log of 1, which is 0, and log here of log of 1, which is 0. So if we put t equals 0, we get 0 in both sides, so f of 0 is 0. Trying to estimate f, and it starts here. Now what happens if we take the derivative of f? So f prime of t, it's gonna be, so there is this minus here that's gonna cancel with the minus here. It's just gonna give, so I'm not gonna make the full calculation. It's just the log of p q minus t over q p plus t. There is also this nice symmetry, just taking these exponents and putting it here. And if we again take the derivative and evaluate at 0, we also get p over p, q over q, so it's log of 1, which is 0 again. So now this function is quite flat and around 0. And then we calculate the second derivative of f. I'm not going to do this, but it's a simple thing to do. And we can bound it by minus 4. So it actually has a concave type of behavior, and by having the second derivative be bounded above by -4, we know that by Taylor's theorem we have that f of t is smaller or equal than -2t squared. So we just can evaluate f by looking at the one of the form of Taylor's theorem that uses some theta between the point where you're expanding and the point where you want to evaluate, and write f of x as 0 plus 0 plus f double prime over 2 of some value theta. Since this is smaller or equal than 4, we get theta, sorry, and there is a theta square here, x square here. So you get smaller or equal than 4 minus 4 over 2x squared. So in the end, we have finally obtained the bound that we want, because since f is the log of this, if we come back to where we were, the deviations bound, this is just e to the f, the bound on e to the f. So this 2t is exactly what we were looking for, and we proved this deviation bound. So this is just an example of how you can drop the requirement of the variables to be IID, and how you can use the fact that they're bounded to obtain directly an explicit bound on the exponential moments. But what I would like to finish is to say that this is something that it's actually useful in applications, because when you talk about the law of large numbers, right, that says that xn over n converges to something, it's not going to give you the rate of convergence. So if you say to a statistician, if you want to know the result of an election, just ask enough people and they're gonna give you the answer, say 0 or 1, 0 if they're voting for some candidate and 1 if they're voting for another candidate, and just sum, and this will converge. But the statistician will not just want to know that it eventually converges, it wants to know what's the probability that you're making a mistake. And they don't want a probability of the size smaller or equal than e to the minus theta n. If you don't know theta, this is also useless. But this is giving you something that's explicit. What we sometimes call this in concentration theory is that this is a non-asymptotic bound. We are not taking n to infinity, not taking t to anything. This inequality holds for every n and for every t. So this is the beauty of concentration inequalities in a way, and they turn out to be very useful. In particular, let's just finish in mentioning that this gives us a law of large numbers for free. So if, this is a nice observation, if the probability that xn minus np be larger than nt decays as some sort of exponential, then this event for every t, right? This event we call an cannot happen infinitely often, because this is summable. So by Borel-Cantelli, what we know is that the probability that an happens infinitely often is 0. So in particular, we know that xn over n converges almost surely to p. So large deviations or concentration inequalities can give you for free a strong law of large numbers. Of course, the law of large numbers that we saw in probability 1 had very weak regularity assumptions on x, or on psi if you prefer. So this is a very weak assumption, while for concentration inequalities we are assuming something like this, which is much stronger. But in any case, this type of concentration inequalities implies the law of large numbers, and in several situations it can be proved for non-IID random variables. So this is the beauty, that we're getting law of large numbers even for variables that are not IID.